Okay, so in the previous analysis video, we saw the notions of limit superior and limit inferior of a sequence of real numbers. Now, just like in case of supremum and infimum of a sequence of real numbers, there you may remember that we used moving pistons to understand those concepts. So a similar thing can be done here also for limit superior and limit inferior. To understand the limit superior of a sequence, you start with a piston at plus infinity moving leftward, and the piston has this tendency of moving leftward, and it will continue to do so if it does not encounter any obstacle, and that obstacle will be created by the terms of the sequence. So the piston will move leftward, will keep on doing so until it is stopped by the presence of the sequence. So if it encounters some term of the sequence along its journey, it stops there. The place where it stops is the supremum of this sequence, which is just the ordinary supremum, and which in our new notation is A1 plus. Now we start removing terms from the sequence. We first remove the element A1. Terms and elements are used synonymously, okay? They just mean the individual elements of the sequence. Now if we remove A1, then this may cause the piston to slip leftward. We have already seen in some of the examples in the previous video that even after removal of A1, the supremum may not change, but it may change also. That's why we are saying this may cause our piston to slip leftward, thus changing the supremum to a new position A2 plus. According to our notation, A2 plus is the supremum of this sequence, which is obtained from this sequence after removal of A1. That's what the author writes here. Though in many cases the piston will not move and A2 plus will just be the same as A1 plus. We have seen this in the examples. Then we continue this removal. We then remove the second element A2, causing the piston to possibly slip a little more leftward, okay, towards the left, giving rise to the new position A3 plus. Possibly again we are saying because it may not move. If we keep doing this, the piston will keep slipping, but there will be a point where it cannot go any further, and that point is the limit superior of the sequence. And similarly, you can also understand limit inferior using pistons. For that, you start with a piston at minus infinity moving rightward, and similarly you can understand the thing. Now after this, we have the proposition which gives us some of the properties which follow somewhat immediately from the definitions of limit superior and limit inferior, and they are very fundamental. So let us see the proposition. And it's a useful proposition also. We will use, it has some parts, we will use those parts to our advantage. Let an varying from m to infinity be a sequence of real numbers. then these quantities, let L minus be the limit inferior and L plus be the limit superior. Okay, they have written L plus first, it does not matter, it means the same thing. Be the limit inferior and L plus be the limit superior of the sequence. Okay, just to remind us of what these things are, Tau writes thus: both L plus and L minus are extended real numbers. That is, we should not forget that these quantities may be plus or minus infinity, any one of them. They are not always real numbers. Okay, then the following things are true. Part A, for every x greater than L plus there exists an integer n greater than or equal to m, because that's where the index of the sequence starts, such that the nth term of the sequence is less than x for all n greater than or equal to n. In other words, this thing can also be expressed in words. For every x greater than L plus, the elements of the sequence are eventually less than x. Eventually less than x because starting from this index, all the terms are less than x. So what it means is this: say you have the sequence on the real line, because after all it's a sequence of real numbers, and you have the limit superior here somewhere. Okay, and your x is greater than the limit superior, then there you will get a stage in the sequence such that after that stage all the terms are going to be these terms an plus 1 etc. They are all going to be less than x, which means that at most finitely many terms are possibly greater than or equal to x. That's what this means. And there is another similar one involving the limit inferior. Similarly, for every y less than L minus, there exists an n greater than or equal to m. Just ignore these lizards and other disturbances, okay? Can't do anything about them. Such that this time an is greater than 1. Okay, so this is part A. There are others. B, for every x less than, this time less than L plus, and every integer n greater than or equal to m, there exists an integer n greater than or equal to capital N such that an is greater than x. In other words, for every x less than L plus, the elements of the sequence exceed x infinitely often, okay? Exceed x infinitely often. Often, some of you would say. Similarly, and then the corresponding one for limit inferior, for every y greater than L minus, oh, I should have been more careful because now I have run out of space. But you have already seen these parts, so there is no harm in rubbing them off if I have to. Okay, so when we are going to prove them, then we will recall the parts individually. So for every y greater than L and every integer n greater than or equal to m, there exists an n greater than or equal to n such that an is less than y. So what this says, let's just see what this says on the real line. For the limit superior at least. So this is our real line and we have L plus here somewhere. And now our chosen extended real number x, keep in mind that x is not necessarily a real number, x is an extended real number. X may very well be minus infinity also. So x now lies to the left of L plus. Now what this part says is that if we find we have chosen x, now if we also choose a stage in the sequence, that is our terms of the sequence or elements of the sequence are like this. Say we have chosen a stage capital N. The sequence continues after that stage also. Then you will get some element of the sequence here after this stage, or maybe here itself, so that that corresponding n, say an, is greater than x. That is, that an will lie here. It will lie to the right of x. And the stage is your choice. You may then you may decide to choose an even larger n. Then also from that stage onwards, you have the terms in the sequence. Among those terms, you will still find some an that exceeds x. So that's why, in other words, for every x less than L plus, the elements exceed x infinitely often. Infinitely often because the stage from where you want that element which you want to exceed x, you want that element, that stage is your choice. So you can choose such stages infinitely often. So correspondingly there will be infinitely many ans that exceed x. So the sequence exceeds x, you can say somewhat vaguely, the sequence itself exceeds x infinitely often. And similar interpretations are also there for the parts involving limit inferior. Okay, then part C. In part C we have this inferior, this is not inferior, this is infimum. Infimum of the entire sequence is less than or equal to the limit inferior. The limit inferior is less than or equal to the limit superior, which in turn is less than or equal to the supremum of the entire sequence. These inequalities are always true. Then part D. If C is any limit point of the sequence, then C lies between L minus and L plus. E. Part E says that if these limit superior and limit inferior turn out to be finite, that is, if none of them is plus infinity or minus infinity, then they are limit points of the sequence. If L plus is finite, if the limit superior is finite, then it is a limit point of our sequence. Similarly, if the limit inferior is finite, then it is a limit point of the sequence. So it means that if our limit inferior and limit superior are finite, are real numbers, then they are limit points. That's what part E says. But then combining this with part D, you get the fact that in that case, the limit inferior is the smallest possible limit point and the limit superior is the largest possible limit points. Any other limit point that the sequence may have will lie in between them. And finally, there is another part F. This is very important. Let C be a real number, ordinary real number. If our sequence converges to C, then C is equal to the limit inferior and C is also equal to the limit superior. So that means in this case the limit inferior and the limit superior are forced to be equal to C, and hence they are in particular real numbers. Okay, so for a convergent sequence converging to some real number, of course, limit inferior cannot be strictly less than limit superior. In general, this inequality is true, but you cannot have strict inequality if the sequence is convergent. You can guess immediately some things about these facts. Recall that we already know that a convergent sequence of real numbers is a Cauchy sequence, and we have proved that Cauchy sequences are bounded. So because the sequence is bounded, these things will be real numbers. And why I am saying that is true, it is because you look at these inequalities. If the sequence is bounded, then its infimum is a real number and so is its supremum. So these quantities are forced to be real numbers as well. So at least they are real numbers, but additionally it turns out that they are actually equal and they are equal to the limit of the sequence. But the even more important part, there is the converse is also true. That is even more important. Conversely, if L minus is equal to C is equal to L plus. Keep in mind that C is a real number that has already been chosen. So these equations mean that L minus and L plus are equal, and that too not just in any way they are equal to a real number. So that means they themselves are real numbers. Then our sequence converges to C. So these are all the parts in the statement of this proposition. Let us now prove this. Right now we are going to prove only parts A and B. The other parts will be proved in one of the exercises at the end of this section. Parts A and B, you will see you don't have to actually do anything, just you keep on using the definitions of the various parts in the definitions of limit superior and inferior, and you will get parts A and B. But now because we don't have the statements with us, we have to recall them. So in the beginning of part A, what we have to prove is this. We are given that x is greater than L plus. Then we have to prove that there exists an integer capital N greater than or equal to m, the smallest index of the sequence, such that the terms an are less than x for all n greater than or equal to n. That means the sequence is eventually less than x. So let's now see. This is given to us. We have x greater than L plus. Let us now write what L plus actually is. It is the limit superior, which means that this is the infimum of this sequence, an plus. Let's also recall what the terms an are. I mean an plus. An plus is defined to be the supremum of this sequence. In other words, it's the supremum of this sequence. That is, if we somewhat loosely write the sequence, that's what an plus is. And the infimum of all such an pluses, all such suprema, is the limit superior. Okay. So what do we see from this? X is greater than the infimum of a sequence. Infimum, you recall, is also the greatest lower bound. X is greater than the greatest lower bound. So that means x cannot be a lower bound of this sequence because it's greater than the greatest possible lower bound. Which means, in fact, let us, should we write those things, x is the greatest? It's understood, no. We can directly write thus, x is not a lower bound So x not being a lower bound means what? For x to be a lower bound of this sequence, we should have had this. For all n greater than or equal to m. This statement is not true because x is not a lower bound. That means there should be at least one n greater than or equal to m for which x will be greater than an plus. Okay, so x not being a lower bound of this sequence now means this. This implies that there exists an integer. It is understood n is an integer. We don't have to write those things explicitly. Such that x is greater than an plus. X is greater. Okay, let's just write it nicely here. And an plus is what? An plus is the supremum of the sequence that starts with capital N. That means all the terms in that sequence are of course less than or equal to this supremum, which is by definition the supremum is an upper bound. It's the least upper bound of for those terms. Since an is less than or equal to an plus for all n greater than or equal to n, we have an is less than or equal to this, and this quantity is strictly less than x. So using transitivity and all the other properties of order, an will be less than x for all n greater than or equal to n. That's what we wanted. So the sequence is eventually less than x. And note one more thing, that you may see that we are somewhat carelessly using all possible properties of order. We are justified to do that because in the extended real number system also we proved that the ordered relation satisfies all the properties that the ordinary ordered relation on R has. Okay, so we are justified in going like this. There is no problem. All the subtleties of having plus infinity, minus infinity in these inequalities somewhere, they have already been taken care of previously in the previous sections. Okay, so that means we have proved half of part A. The other half involving limit inferior can be similarly handled, but let's just do that and see what we get. Next, we have y, I believe, is less than L minus. Yes. So L minus is by definition the supremum of this time this sequence of infima supremum means least upper bound. Y is less than the least upper bound, so y cannot be an upper bound for this sequence. So there exists some index n greater than or equal to m, of course, such that for y to be an upper bound of this sequence, y should have been greater than or equal to all a n minus s, but that is not going to happen because y is not an upper bound. So y will be less than at least one a n minus. But a n minus according to us is itself an infimum, since a n minus is equal to infimum of this sequence. We have y less than a n minus less than or equal to a n for all n greater than or equal to n. Being the infimum of this sequence, this is going to be less than or equal to all the terms or all the elements of the sequence. So that's what we have written here. That is, y is less than a n for all n greater than or equal to n. Y is less than, yes, a n is greater than y, same thing. Then we move to part B. Okay, this time what we are given is this. X this time is less than L plus, x less than L plus, and n is some integer greater than or equal to m that has already been chosen. Okay, from x less than L plus, which is infimum of this, okay, what we have from here, we have, since infimum of this sequence is a lower bound, it's the greatest lower bound, but after all it's a lower bound, so the infimum is going to be less than or equal to all the terms of this sequence, and x is less than the infimum, so x is going to be less than a n plus for all n greater than or equal to n. Or we may confuse ourselves here, that is, this n may clash with this. Okay, let me just use something else. am say. So note that we are allowed to because this is true for all m greater than or equal to m, so we are allowed to take n in place of m. So in particular, x is less than an plus, and let us now just use the definition of an plus itself. It is the supremum of this sequence okay. Now supremum means least upper bound, and x is less than the least upper bound of this sequence. So that means x itself cannot be an upper bound of this. This implies x is not an upper bound of this sequence. So there exists an integer such that the corresponding an will exceed x, because x is not an upper bound. And that's how the sequence exceeds x infinitely often, and the stage that we have chosen here is our choice. You can choose this capital N to be very large also, then also you will get some index even greater than that or maybe equal to that choice, such that the corresponding term in the sequence exceeds x. So you choose different capital N's, infinitely different capital N's, infinitely many times you will exceed x. You will make the sequence exceed x. Now the inferior part. Next, let y be greater than, everything will be opposite, y is greater than L minus, and n is again some chosen index greater than or equal to m, from y greater than L minus. L minus is the limit inferior. So this is the supremum of this sequence of infima we have. So this is the supremum of this sequence. That means it will be greater than or equal to all the terms of the sequence. So correspondingly y is also greater than am minus for all n greater than or equal to m, this is comma, okay. In particular, we have y greater than an minus. Now an minus is the infimum of this sequence. Infimum means greatest lower bound. Y is even greater than that, so y cannot be a lower bound of this sequence. Thus y is not a lower bound for the sequence this. So y will not be less than or equal to all the terms of the sequence. There will be at least one term in this sequence that will be less than y. So there exists some n greater than or equal to n such that y is not lower bound. That means an is less than y. Okay, and have we? Yes, we have got what we wanted. Parts, the other parts will be proved in the exercises, but which exercise? Third one. Parts C, D, E, F will be proved in exercise 6.4.3. So this completes the proof of this proposition in an incomplete manner, that these things are yet to be done. Now after this, the author writes something about the parts of this proposition, which we have already said, but anyway, let's just write them down. Parts D and E of the above proposition about that limit superior and limit inferior becoming limit points say in particular that L plus is the largest limit point. And L minus is the smallest limit point. Provided L plus and L minus are finite, that is, provided they are real numbers. And also part F, what we were saying is so important. says that if L plus and L minus coincide, but not just in any manner, that is, for example, part F won't say anything if L plus and L minus are both equal to plus infinity. That may happen. We have already seen in the previous examples when we were looking at the examples. Then we cannot say that the sequence is convergent. Only when they coincide and become a real number, then part F says that the sequence is convergent. The sequence converges. So that means we have now obtained a new technique of showing that a sequence is convergent. This gives us a way to test if a given sequence of real numbers is convergent. Compute the limit superior L plus and the limit inferior L minus, and see whether they are equal to a real number. Now after this there is a lemma, a result which the author has named comparison principle. It will help us compare to sequences which are already comparable. Let's just see the statement that will make these remarks clear. That means if two sequences are comparable term by term, then their suprema, infima, limit superior, limit inferior, they are also comparable. Suppose AN and BN are two sequences of real numbers. Such that AN is less than or equal to BN for all indices N. This is expressed by, that's what we meant when we said that the two sequences are comparable term by term. Then the following inequalities hold. First of all, infimum of the sequence an are we given an less than or equal to? Yes, it does not matter if even if you write greater than or equal to, nothing actually changes essentially. Infimum of bn, then supremum of an is less than or equal to supremum of bn. Then the limit inferior of an is also less than or equal to the limit inferior of bn, and you can guess the next one, it has limit superior. Limit superior of an is less than or equal to limit superior of bn. This we are not going to immediately prove, we will see in the exercises its proof. There are, let me digress a little bit. When you are going through something, not just in mathematics but anything, there are two different ways of looking at things. One is your global way, which gives you a bird's eye view of the entire thing through which you are going. When you do that global reading, you don't go through proofs. For mathematics in particular, I am saying, you don't go through proofs means you don't look at the finer details. You just see where the results are, what the results are, and how the results are related to one another. You see the network of results. So in your mind, you get to see the big picture. But then when you do the local reading, you concentrate on each result and see why that result is true. Inside that result, then you see what is going on. If you do these two kind of things, one after another, in a maybe back and forth way, as is convenient to you, you will see that you ultimately will get a much better understanding of the whole thing. You will know the finer local details. Also, you will have an idea of what is going on when you zoom out. Okay. So the practice of Tao, not proving these things, forces us to prove them afterwards. So we get a chance of looking at what the things are. So right now we are going through, although we have already seen one local thing, that is, we have proved something of one theorem or one proposition, but now you see this result, and immediately after seeing the result, if you start proving it, you will that thing will be gone, that global view will be gone. So it's according to me, it's better to first of all in a given section see what the results are, what they mean, what the statements mean, and how they relate to one another, and then you look at each individual proof separately. Now this result has a corollary six, 4, 14 will be, and it has a name also. It's called the squeeze test. This is somewhat like a result with which you may be already familiar, the sandwich theorem from calculus, that thing. But for sequences, let an comma bn and cn be sequences of real numbers such that an is what is given. It does not really matter what is given, but let's write what the author has written. An is less than or equal to bn and bn is less than or equal to cn for all n greater than or equal to n. So the terms of the sequence bn are sandwiched in between the corresponding terms of the sequences an and cn, or squeezed in between them. Now if these two sequences converge, then they will force the intermediate sequence to also converge. Suppose also that an and cn both converge to the same limit. Say L. Converge to the same limit means L has to be a real number. Okay, keep that in mind. Then Pn also converges to L. That is the squeeze test. For this one also the proof we will see later. This is the fifth exercise. Now an example. We already know in fact this we proved this in this proposition 6, 1, 11 that this limit is 0. This limit in particular is used so much in the study of analysis that after some point it becomes almost natural. It seems like it has to be 0, it cannot be anything else. That is also the case with, in fact, anything in mathematics. See it often, many times it becomes natural. Of course, it has to be something correct. Now, by the limit laws, which is proposition, it was theorem 6, 1, 19. This also implies that limit of the sequence 2 divided by n is 0 and limit of this sequence is also 0. In obtaining these two limits, what we did is we multiplied the sequence 1 over n by the constants 2 and minus 2. The speech test then shows that for any sequence Pn of real numbers for which these inequalities are true. Minus 2 over n is less than or equal to Pn, which is less than or equal to 2 over n for all positive integers n limit of Bn must be equal to 0, because these two limits are 0 and Bn lies in between the nth terms of these two sequences and they are converging to 0. Let me pour some ink in this. Okay, for instance, using this technique, we can use this to show that this particular sequence minus 1 to the power n divided by n plus 1 over n square is convergent to 0, it converges to 0, or that this sequence 2 to the power minus n converges to 0. Note that we can use induction to prove this for all positive integers n. So for this sequence, the left hand side sequence, the sequence an can be taken as the constant sequence 0. All of those terms are equal to 0. And the right hand side sequence cn can be taken as the sequence 1 over n, the sequence of reciprocals of positive integers. 2 to the power n is trapped in between these two, and this of course converges to 0 because it's the constant sequence, and this we already know converges to 0. So the squeeze test forces this intermediate sequence to also converge to 0, and this one can prove easily by induction on n. The first inequality we already know, keep that in mind. It's a power, here 2 is a positive real number, and whatever the exponent is, this power is always greater than 0. After this there is a remark about the things we have got so far regarding convergence. The squeeze test combined with the limit laws and the principle that monotone bounded sequences always have limits. We have in fact obtained quite a few results by now. Monotone bounded sequences. Using all these things, allows us to calculate many limits. To compute a large number of limits. And this we will see in the next section and in the next chapter also. Next chapter, fine, but in the very next section after this, that is 6.5, is about limits, some standard limits. So there also we will see some particular sequences and their limits. Now, there is a corollary of the Swiss test, and that corollary itself also has a name. It's known as the zero test for sequences. Its statement goes like this: it becomes important in several situations where the limit of the sequence is 0. That's why it has the name zero test for sequences. And the test is just this: let be a sequence of real numbers n is convergent with limit 0 if and only if. Maybe the language is slightly different in the text, but the meaning should be the same. We can write it in whatever way we want. Is convergent with limit 0 if and only if this sequence is convergent. We obtain this sequence from that one by taking absolute values of the elements of the original sequence. Its proof also we will see in the exercises, and that is the 7th exercise. Okay, now we come to a result which will give us a reason for having real numbers and why we have gone through so much effort to construct real numbers from the system of rational numbers. It has the name completeness of the reals, and actually this theorem, its statement is just this: a sequence of real numbers is convergent if and only if it is a Cauchy sequence. Note that we have already proved one half of this theorem, namely that if you have a convergent sequence of real numbers, then it has to be a Cauchy sequence. Now we are going to prove the converse, and both the direct implication and the converse, they constitute the theorem, and in its proof we will use the tools of limit superior and limit inferior. And we are actually going to prove it now. Completeness of the reals. and the statement is just that what I have said right now. A sequence an, the author has taken n equal to 1. We have seen that where you start the sequence index, it does not really matter. A sequence, it does matter in fact, but as far as limits and other things are concerned, the things we are dealing with here in analysis, there the starting point does not matter. A sequence of real numbers is convergent if and only if it's the Cauchy sequence. Now, immediately after the theorem, there is a remark, and after that we have the proof. Note that while this is very similar in spirit to proposition 6.115, proposition 6.115 has the title formal limits are genuine limits. Recall what it was. It is a bit more general. Because there we had a sequence of rational numbers, but here we have a sequence of real numbers. Since proposition six one of 15, that one refers to Cauchy sequences of rationals. Rationals instead of reals. Okay, let us quickly go through the proof. We will understand the steps. Proposition 6 112 in the beginning section itself already tells us that an is a Cauchy sequence if it is convergent. So we now prove the converse. I'm not exactly writing what is written in the text, okay? I mean the language. So let an, we are already given that an is a sequence of real numbers, so no need to mention that again. So let this be a Cauchy sequence. That is now our hypothesis. We are now going to prove that it is convergent. So the thing we immediately notice is that Cauchiness implies boundedness from a previous result. That result is precisely this. We know from Corollary 6.117 that our sequence is bounded, and because the sequence is bounded, its limit superior and limit inferior are both real numbers. They cannot be infinite, and that in turn, that actually follows from this. So by lemma 6.4.13, which is the comparison principle, I believe, if I am correct. Yes. Or proposition 6.4.12, properties of limit superior and inferior, part C of that proposition. This implies that the limit inferior, which is supremum of an minus and the limit superior, which is the infimum of the an pluses, are both finite. That is, they are both real numbers. Okay. Now our aim is to, our strategy is to prove that these two things are actually equal, because then already we have both of them real numbers, they are not infinite. So now if we can prove that they are equal, then by part F of proposition 6.4.12, the sequence will be convergent and it will have this common real number as limit. Okay, so that's what we now plan to do. So we start by choosing epsilon. So let epsilon greater than 0 be any real number. So epsilon is any positive real number. Now we have used Cauchiness of the sequence once, namely where we concluded that because the sequence is Cauchy, it is bounded. But now we are going to use the fact that the sequence is Cauchy itself. We are going to use the definition of Cauchiness, since this is a Cauchy sequence, there exists an integer n greater than or equal to 1 such that the distance between an and am is less than or equal to epsilon for all n and m greater than or equal to n. In particular, we have an minus, let me write it here, an minus a capital N, because we can choose small m equal to capital N for all n greater than or equal to n. That is, an minus epsilon is going to be less than or equal to an, which is less than or equal to a capital N plus epsilon. These inequalities are equivalent to this one for all n greater than or equal to n. Okay. Now, what do these inequalities imply? This implies that, okay, now since the index is starting from capital N, we are saying something about this sequence. In these inequalities, what we are saying is that a capital N minus epsilon is a lower bound of this sequence and a capital N plus epsilon is an upper bound of this sequence. So that's why we obtain this an minus epsilon is less than or equal to infimum of this sequence, which is less than or equal to supremum of this sequence, and that is less than or equal to an plus epsilon. Why? Because this is some lower bound of the sequence an, where n is starting from capital N, and infimum is the greatest lower bound. So infimum is greater than or equal to this some lower bound, and we already know that infimum is less than or equal to supremum for any sequence. There is one situation where infimum of a set becomes greater than supremum, that is for the empty set. But since a sequence has elements in it, it is non-empty, so always for a sequence infimum is less than or equal to supremum. Just like that, this an plus epsilon is an upper bound of this sequence and supremum is the least upper bound. So this least upper bound is less than or equal to some upper bound. So we have obtained these inequalities. Hence, by proposition 636, go to this proposition and see what it says. Or one can also use the comparison principle, lemma 6 for 13. No, we don't need this lemma here. We need only this proposition. What do we get now? It implies an minus epsilon is less than or equal to the limit inferior, and this is less than or equal to the limit superior, and okay, now what? Now note that infimum is itself less than or equal to limit inferior, and that follows from part C of proposition 6 for 12. Just like that, supremum is greater than or equal to limit superior, and these two things are in this relation to each other. You just go to proposition 6 for 12 part C, you will understand where we are getting these inequalities from. Okay. Now if we consider this difference L plus minus L minus, L plus is less than or equal to An plus epsilon, and this difference is of course non-negative because of this middle inequality. Now this is L plus is less than or equal to An plus epsilon, and L minus is greater than or equal to An minus epsilon. So minus L minus is less than or equal to minus of An minus epsilon, and you see that this becomes 2 epsilon. Okay, so this lies between 0 and 2 epsilon. Since epsilon is arbitrary and L plus and L minus do not depend on epsilon, we must have L minus equal to L plus, that is, this should be 0. If on the other hand, if you are finding this difficult to believe, then you would of course suppose that L minus is strictly less than L plus, then choose this particular epsilon, L plus minus L minus divided by 3, to arrive at a contradiction. Use this epsilon value here in these inequalities, you will see that you arrive at a contradiction. Hence, by proposition is that 12? Yes, 12f An is convergent. So this completes the proof, and it shows that Cauchiness and convergence are synonymous when we are talking about sequences of real numbers, which however is not the case for rational numbers. We have already seen that. Let me just see one thing. Okay, it is still recording. That means I have not run out of space. Shall I write the remark also after this? So this will complete this section, and in the next video we can solve the exercises. In the language of, we will see these things, okay? In the language of metric spaces, see chapter 12. Theorem 6 for 18 asserts that the real numbers form a complete metric space. There are no gaps or holes, that they do not contain holes the same way rational numbers do. Certainly the rationals have lots of Cauchy sequences which do not converge. Other rationals, for instance, the terms of this sequence converges. This is a sequence of rational numbers, but it converges to the irrational square root of 2. This property is closely related to the least upper bound property, which is theorem 559. We have seen this, and is one of the principal characteristics in which reals are superior to rationals. For the purposes of analysis, that is taking limits, derivatives, integrals, finding zeros of functions, considering maxima, minima, things that we normally do in analysis. Zeros of functions. That kind of thing. As we shall see in later chapters. So this completes this section, and it completes the video also. Today is 13th, huh? 14, 15, 16. So, oh no, what the hell am I saying? This is not following the usual cycle. So analysis means it will come every Sunday, and tomorrow we have Galilean's algebra exercises, and also some results as one of you has requested. So that will be all in this video. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.